We will demonstrate that roots of polynomials with real coefficients come in conjugate pairs. So we will let P of z be a complex polynomial with real coefficients. So it will have some degree, so say n. So the first term is a sub n times z to the n. And then the second term we'll call a sub n minus 1, z to the n minus 1, etc. Down to a1z plus a0, where the coefficients a sub I are real numbers for I equals 0, 1 up to n. And the complex variable z is x plus iy, where x and y are real numbers. So suppose that alpha is a root of the polynomial p, which means that p of alpha is equal to 0, which can also be written as a sub n alpha to the n plus a sub n minus 1 alpha to the n minus 1, etc. Alpha a1 alpha plus a0 is equal to 0. So we've plugged alpha into the polynomial, and it's a root, so we get 0. Now we would like to show that p of alpha bar, the conjugate of alpha, is also equal to 0. So to that end, p of alpha bar, plug alpha bar into the polynomial here. It's a sub n alpha bar to the n plus a sub n minus 1 alpha bar to the n minus 1 on down to a1 alpha bar plus a0. We would like to show that this is equal to 0. So that's the question. Does that equal 0? We will use the property that the product of conjugates is the conjugate of the product. I'll write that here. We've seen that z1 times z2 quantity conjugate is equal to z1 conjugate times z2 conjugate. And this is true no matter how many factors we have. The rule displays 2 factors, but there could be more than 2. As long as there's a finite number of factors, this rule applies. And we're going to use this rule, in this case, from right to left, because we have alpha bar to the power n, which is alpha bar times alpha bar times alpha bar n times. And according to this property, then, we could just put the bar over the product of all of the alphas. So using exponent notation, this is a sub n times alpha to the n quantity bar. This would be alpha to the n, and there's the bar on the top. And we do this for each term. So the next term would be a sub n minus 1. Then we have alpha to the n minus 1 quantity conjugate. The conjugate of the product is the product of the conjugates. And then this one we can leave alone. Now we will use the conjugate of a sum as the sum of the conjugates. z1 plus z2 quantity bar is equal to z1 bar plus z2 bar. And we will again use this one from right to left, and with n plus 1 terms instead of just 2. So notice here also that the coefficients are real numbers. So since the coefficients are real numbers, that means that each coefficient is equal to its conjugate. The conjugate of a real number is itself. So in other words, this a sub n can be written as a sub n bar. Let's do that. So all of these conjugates can be written, all of these coefficients can be written with the conjugate bar on the top. A1 conjugate, alpha conjugate, A0 conjugate. And now we'll lump these together using the product property of the conjugate. So this is, the first term is an alpha to the n quantity bar. And we do that for each term. An minus 1 alpha to the n minus 1 quantity bar. A1 alpha quantity bar. A0 bar. Now we can use the sum of the conjugates is the conjugate of the sum from right to left. We have a sum of conjugates here, conjugate plus conjugate, more conjugates, conjugate, conjugate. So we can write one conjugate bar over the top of the entire sum. And so we get an alpha to the n plus an minus 1 alpha to the n minus 1 on down to a1 alpha plus a0, and this whole quantity is conjugated. But inside the parentheses here, this is simply p of alpha. This is just the polynomial p of z with alpha plugged in for z. And p of alpha was equal to 0, so this is 0 bar, which is 0. So therefore, alpha bar is a root of p as well. And this is what we wanted to show.